Hi students, so let's come back to this class. So in the first sessions, we have discussed regarding wave functions, and then we have derived a Schrodinger time independent wave equations. In the beginning, just I have told the introductory things about wave mechanical model of the atom. So how that wave equations were derived by our scientists when that material particles means exhibits of wave nature or wave is associated with our what? Material particle. When wave is associated with material particles, then that wave is having what? Some equations. So that was derived by our scientist Erwin Schrödinger. So that equations to describe the behavior, physical behavior of that particle. The solution of that wave is what? Describes the particle is particle aspects or wave aspect, and it also consistent with our what uncertainty principle. Okay. So in this session, so we will discuss regarding the physical significance of that waveform or the interpretation of what is a waveform. So I already have mentioned that in my first class itself. So wave function is a variable quantity. What it does, it describes the what de Broglie waves is called as a wave function. The variable quantity which describes the de Broglie wave is called as a wave function. So that was denoted by a symbol of a psi. Okay. So as I said in my class, in the first class, the value of the wave functions associated with a moving particle at the particular point in space at time t finds the what? The particle at that instant. So what it does, what it gives. So whatever the value of that wave function is there, which is associated with your moving particle. So at some particular points in space, x, y, z in time t, so will give us what? Will find the particle at that point. Okay, so that's what importance of our wave functions. Okay, and it means so this gives the complete information about the state of the your what physical system at a particular time. So it's also called it as what state function, and it represents the what probability amplitude. It represents what a probability and amplitude. Okay, so here if the value of your psi is whatever you obtain, value of your wave function is large, then the probability of finding the particle is also large. That is, the chance of finding the particle at that point is what is at what time when the wave function is at is what is large. Suppose if psi is small, then probability of finding the particle is so small. The wave functions will give us the likelihood of finding the particle at a given instant at a given position. Okay, so this is something that I have told in my first class. So in this class, we will discuss about a wave function and its significance. So the meaning of wave function, as already I have mentioned in my first class itself. Now we will discuss what are the physical significance of this wave function. Okay. So as I said that in your previous class, the variable quantity is what it is describing or characterizing a de Broglie waves is nothing but a what is a wave function. That's also a function it is. and the probability of the finding the particle. The value of psi is lot. The probability of finding the particle in a space at a particular point is what is log. Okay, so here the probability of finding the either what is wave functions. The probability of finding the a particle by the or you can say that is just the probability of finding a particle is described by the wave function psi. That's also the same thing, psi, and it is proportional towards a psi square. A psi square. It's proportional to what? The magnitude of a psi square. Okay. Here the what is that magnitude? The square of the magnitude of the wave functions psi. The probability of what finding the particle is described by the wave function psi, and it is proportional to what the square of the magnitude of that wave function. So here the square of the magnitude of wave function is nothing but will give us what the probability density. Okay, so probability density is nothing but the probability of finding the particle is described the wave function psi, and that is proportional to the square of the magnitude of what of wave function. Here, the magnitude of psi square is nothing but what the probability and density. Okay. Next, suppose you can write this probability density in another way. It's what is the probability density if psi is complex, that the wave function is complex, then the probability density is also designated by psi into psi star. So in the below equations, if psi is complex, then probability density is given by psi into psi star, where psi star is what? Is complex conjugate of what is a star. Psi star is complex conjugate of a star. So this also will give you what the square of the magnitude of or wave function. That's nothing but what the probability and density. Okay. Uh, Suppose if our particles is existing in a three-dimensional space. So in such cases, the probability of finding the particle, what is if the particle is existing in a three-dimensional space or three-dimensional box having a volume element dx, dy, and dz. These are the what? The length of that volume elements along x, y, and z axis. So in such cases, the probability of finding the particle in a volume dx, dy, and dz is designated by is given by the magnitude of the square of the magnitude of wave function. The square of the what? The magnitude of the wave functions into dx, dy, and dz. So we'll give you what? The probability density. So what I'm saying is this if our particle is located in a three-dimensional box having in what the volume element dx, dy, and dz. In such cases, the probability density is given by the magnitude of psi square or the square of the magnitude of the wave functions. So into you want to multiply the what dx, dy, and dz. So which will give you what the probability of finding the particle at a given time in a given position. It's okay. So here, if just that equations, so we are putting it like this: when the particle is existing in a three-dimensional box, so in order to find that the probability of find the particles in a three-dimensional box is obtained by integrating that square of the magnitude of that wave functions over the entire space along x, y, and z axis. So there you are getting what triple integration of what the triple integration of what is minus magnitude of psi square into dx, dy, and dz is equal to what is I unit. The probability of the finding the particles in a volume element dx, dy, and dz on integrating over entire space is equal to what it is? Unity. Unity is that's equal to what? One is. It means the particle is a single one. That is in which that wave is what? Associated with it. Okay. So if the any wave functions satisfy the equations, integration of what is? Integration over entire space x, y, and z into magnitude of psi square dx, dy, and dz equals to 1, then such equations are called as normalized wave function, and the condition is called as what? Normalized condition is. Okay. So in order to what? Satisfy the wave functions, in order to satisfy that given what? Normalized wave functions, the psi should or must have what? Following conditions. The wave function psi must have the what? Following conditions. What are the conditions for our wave functions? So in order to obey, they will what? Satisfy our normalized wave function. So what is normalized wave function? The probability of finding the particles is obtained by integrating the wave functions. The integrating what? The square of the magnitude of the wave functions over entire space or all space must be equal to what? A unity. So that integration of magnitude of sine square into dx, dy, dz equals to 1. The wave functions which are satisfied these relations are obeys these equations are called as what? Normalized wave function, and the condition is called as normalized condition. Okay. And what are the wave functions should obey the some following conditions? So what are those? So here the psi must be finite. The wave function, whatever the psi is there, it should be finite for all values of x, y, and z. So whatever the value of psi is there, it should be finite or discrete for all values of x, y, and z. And it should be the other conditions is what the psi must have the what? Must be what? Single value. Single value for each set value, for each set of values of x, y, and z. So psi must have an unique values. Okay. Next condition is what? Psi must be continuous in all regions except in these where the potential energy is what is unified. So these are the what? Different conditions for our what? Our wave functions. Okay. Next, this wave functions are significance of wave functions was explained by our scientists Heisenberg and Bohr. So what are the interpretations regarding the wave functions? Let's discuss that one. Okay. So here, initially, the wave functions was explained by our scientists as Schrödinger. Initially, the Schrödinger has tried to explain the wave functions in terms of what is a charge density, in terms of what is a charge density. So it's in terms of what? A charge density. So in any electromagnetic system, the energy density, that is energy density is nothing but what? That is energy per unit volume is equals to what? X bar. Where what is S? What is A? Where A is what? The amplitude of the wave. Next to and number of photons per unit volume is given by A square divided by what? Is what? The number of photons per unit volume is given by A square by h nu, where h nu is a constant. Okay. So the photon density, which is nothing but what? Constant. The Planck's constant and frequency of our what? Photon is. That becomes constant. So the photon density is directly proportional to what is what? A square. Is directly proportional to what? A square. So see here, our scientist Schrödinger try to explain the wave functions by taking what? Charge density in any charge density. So in any electromagnetic system, the energy density, uh, that is energy per unit volume, is equal to what? A square. And the number of photons per unit volume is given by A square by actually, where the actually is a constant, and so that number of photons per unit volume. Okay? Same thing. So you have to explain wave function also. If psi is the what amplitude of the matter wave at any point in space, the particle density is proportional to what? Psi square, as similar to that of the what? A square, the charge, and charge density. Here is what? Particle density. Particle density is proportional to what? A psi square. So thus the square of the absolute value of psi square is a measure of what? Of particle density. So whatever the square of the wave function is the measure of or what? A particle density. This is the main reason for what? A particle density. Measure of the particle density. Okay. So next is if what? Small e is the charge of the particle, then psi square into E will give us a charge density. Whatever E is there, is magnitude of what? Charge of a particle. And then psi square into E, so will give you what? Charge density. So psi square is a what? A measure of charge density. Psi square is measure of charge density. Later, uh, satisfactory, a complete explanation was given by Max Born in 1926, and that was elaborated by Heisenberg and Bose. According to them, psi square. So in case of above concept, psi square is a measure of charge density, but according to them, psi square is does not measure the particle density at any point, but gives the probability of finding the particle at that point in a given instant of time. This is not a what? A measure of this density. It does not give what? The measure of charge density, but it will give you what? The probability of finding the particle at that point at a given mobility. Okay. So how to get that quantity? The probability of finding the particle at a given point is proportional to psi square. At that point, the square of the magnitude of the what wave function is called as what? Already you know that the square of the magnitude of the wave functions is called as probability density, and psi is nothing but is called what? Probability amplitude. Okay. According to them, already this one I have told, the probability of finding the particles in an volume, within a volume element dx, dy, and dz is nothing but what? Integration of what? That square integration of that wave functions over the entire space must be equal to what is unity. Is dx, dy, dz over all space must be equal to an what is unity. So now we want to integrate that wave functions, the square of the magnitude of that wave functions over the entire space. That's why it's the entire space. If this particle is in three dimensions, you are getting the triple integrations of what? Psi square, magnitude of psi square, dx, dy, and what? dz equals to what is of what? Okay. The wave functions which satisfy these relations are called as what? Normalized wave functions. The integral of the integral over all space. It is what? The integral over all space must be equal to then what it is. Uh, the integral over all space must be equal to 1. So then if it is given this one, the equation can also put it like integration of psi square dv equals to 1. Or that can also be put it in this case, integration of psi into psi star into dv equals to what is. Okay, whenever this particle is existing, not to find the probability of finding the particle in any dimensional box is obtained by integrating that wave function, the square of that wave function uh, for all the aspects. Okay. Here again, psi star is what complex conjugate of what wave functions. Such wave functions are known as normalized wave functions, and the conditions is known as normalized conditions. Okay, so for doing all these things, the psi must be what obey the following conditions. This one already I mentioned in the beginning. They should have the finite values of along along what x, y, and z axis, and it should be single value, and the time must what continuous in all regions. Okay, so that's about your what wave functions, and like this, our Heisenberg as well as what Max Born together explain the significance of or what of wave function. And normally you can say it like this also in single sentence. So it can interfere with itself. Is the one important point. It can what? Interfere with itself. Next, the wave functions describes the behavior of a single particle and not the statistical distribution of a number of such quantities. Okay, so there's a significance about the functions. The condition for normalized wave functions is they have mentioned that integration of minus into plus infinity psi square dv equals what? 1. So dv is element, the value element where the particle is existing in which dimensions is what is located in. Okay, it can interfere with itself. The wave functions describe the what? The behavior of a single particle and not the what? A statistical distribution of what? Number of such contacts. Okay. And one more thing is that one more condition is the condition for what? Mutually orthogonality of the two wave functions. If psi of m and psi of n are the wave functions of the particles, then the integration of psi star m psi star psi star m into psi n into dt equals to 0, or integration of just interchange the complex conjugate. So psi of m into psi star of n dt is equals to 0. So for m is equals to, for m is not equal to what? N. M is not equal to n. Then the condition is said to be what is a normalized condition for what? Mutually orthogonality of the two wave functions. Those two wave functions what? Mutually orthogonal. At what time? If the psi star gets shifted to the m and n. So initially, so this is the what? Psi star m is the wave function of the particle, m particle, and into psi n. In the second, if it is equals to integration of what? Psi m into psi star of n dt equals 0, so then the condition is set to what? Mutually orthogonality of the two wave functions. Okay. So this is about what? The interpretation of our wave functions, or you can say what? The physical significance of what is wave function. Okay. Thank you.